Question 2. A particle moves along the x-axis so that its velocity at time t for t being between 0 and 6 is given by the differentiable function v whose graph is shown above. So this function v is differentiable, which means it's also continuous. The velocity is 0 at t equals 0, t equals 3, and t equals 5. And the graph has horizontal tangents at t equals 1. So this is kind of a peak point right here at t equals 1 and t equals 4. The areas of the regions bound by the t-axis and the graph of v on the intervals of 0 to 3, 3 to 5, and 5 to 6 are 8, 3, and 2 respectively. At time equals 2, the particle is at x equals negative 2. So this region, I'm just going to highlight it yellow, has an area of 8, and more specifically, it's a negative 8, meaning the function is moving to the left at that point. This region in green, we were told has an area of 3. And then if I drew a straight line down here, let's give it another color, this pink region has an area of negative 2. So that's actually doing a lot of the hard work for us right there. So here's our question. For the interval 0 to 6, find both the time and the position of the particle when the particle is furthest. Part A. For 0 less than or equal to t less than or equal to 6, find both the time and the position of the particle when the particle is farthest to the left. Justify your answer. So I'm looking for when the particle is farthest to the left. So what I'm asking for is to maximize, really it's more minimize because I want to be to the left, minimize position. Okay, I'm going to refer to position as s of t. So if I want to minimize position, then I need to work with s prime of t, the derivative, which is the same thing as my velocity. And I want to know first off, where is my position equal to 0? Because those are my critical values. So looking at my graph or the question, we're equal to 0 at 0, 3, and 5. Now the fact that I'm saying farthest means that I want an absolute minimum. So I'm going to use EVT. Now EVT we haven't talked about yet. EVT is extreme value theorem. It's always a closed interval. So we're looking at an interval AB. You find your critical values, and then you do a t-chart. Needs to be a closed continuous interval. So I have my values here. I'm going to do a t-chart here. My t-chart is going to have my critical values and endpoints, so 0, 3, 5, and 6, because EVT says if it's continuous and it's a closed interval, then your extreme values could be at the endpoints or somewhere where there's a critical value inside the interval. And then what I'm going to check is position. Okay, position is the integral of velocity. So we are essentially saying the integral from 0 to 0 of v of t dt, which is 0. And we know, I'm going to be a little bit more specific here. If we're talking about position, what I wrote and just moved is actually the displacement. So if I want to do the position, I should start with s of 0 plus the displacement. So here's what that looks like. S of 0 is at negative 2 plus the displacement is negative 2. So that's the position of the particle at time 0. For S of 3, I am going to do the value from, or the position, I'm going to say 0 to 3. Which is the initial value, which is negative 2, plus from 0 to 3 is negative 8, which gives me -10. For s of 5, it's going to be, again, that initial value plus the integral from 0 to 5 of v of t dt. So -2 minus 8 plus 3 is -7. And last but not least, I probably shouldn't go that high up, initial position plus the integral from 0 to 6 of v of t dt is -2 minus 8 plus 3 minus 2, which gives me -7 minus 2 is -9. So looking at here, the farthest left our particle will be is happening at t equals 3. And here's my justification. It says justification, so I'm going to say the particle is farthest left when t equals 3 and position is -10. Now, we have not been told that this is a continuous function, but we have been told it's differentiable. Since v of t is differentiable, it is also continuous, because continuous is what allows us to use EVT on the interval 0 to 6. And EVT, extreme value theorem, guarantees an extreme value. Extreme value. Part B. We're going to use the work we did in Part B to help us out here for Part B, or Part A to help us with Part B. So it says, for how many values of t, where t is between 0 and 6, is the particle at x equals -8? Explain your reasoning. So now we're looking at using IVT on our position function. So looking at the fact that we've established from Part A position equal to s of t is continuous on the interval 0 to 6. There will be 3 times when position will be x equals -8. The reason for that, where are these 3 times coming from? When I look at this chart, notice that between the time of 0 and 3, the y values, the position spots, are at -2 and -10. So if my position function is continuous, then my position must have been -8 at some point in there. So that's one time. Between -10 and -7 is the interval 3 to 5. Again, it crosses over -8 in that spot. And last but not least, notice that between -7 and -9 also crosses at -8. So here's what we're going to say again. We established that our position is continuous, and then we can say by IVT, intermediate value theorem, 3 times are guaranteed for position of x equals -8. Between the intervals, I'm not going to say between, I'm going to say within 0 to 3, 3 to 5, and 5 to 6. So I'm using my chart, I'm establishing my different y value intervals, and since -8 falls into the y values of the intervals 0 to 3, 3 to 5, 5 to 6, there's got to be a time in there where the x value, or the t value, excuse me, would also be.